Hi there, welcome to Raelene Maths. In this video, I'm going to take a look at solving nonlinear inequalities. The example I'll look at is x squared greater than or equal to 4. We want to solve for the x values that makes this statement true. There are two main approaches that I take, solving graphically or solving numerically stroke algebraically. In the solving graphically case, as long as we have simple functions on the left and the right of the inequality, then we can interpret the left-hand function as a blue function, we might call that f of x, and the right-hand function as, say, a red function. And what we're going to be doing is comparing the heights of those two functions on a two-dimensional grid. Meanwhile, if we're solving numerically, we want to have a 0 on, say, the right side of the inequality. And so we are going to make a sign chart involving the factors of the left-hand expression or function. And in this case, we are going to compare the function value of x squared minus 4 with the value of 0. Namely, greater than 0 is positive and less than 0 is negative. What we are not going to do is to solve this inequality as if it were an equation. If this were a pure equation without the greater than sign, we could take the square root of both sides. And once we do that, we would get a statement that has x on the left plus or minus 2 on the right. But we can't do this when we have an inequality. The reason why is that an equation always remains true when we perform an operation on both sides of the equation. But that's not always the case for an inequality. In this particular example, if we took the x squared and the 4, I'll just make the x squared the 9 here underneath, and the 4 is still the 4 in red. We see that we have 9 as a representative of x squared, and we could write 9 as negative 3 squared, and we could write 4 as 2 squared. So this first statement is true, and this second statement is still true. Now the purpose of square rooting both sides was to undo the squaring. If we undo the squaring, we get the statement negative 3 is greater than or equal to 2, which is no longer true. The reason is, if we take a look on a number line, we see that negative 3 is to the left of 2, and therefore negative 3 is less than 2 on the number line. We will explore the reason why we can't treat inequalities the same as equations when we look at one-to-one functions. The first method we will take a look at then to solve the inequality is a graphical approach. If the two functions on the left and the right are quite basic or simple functions to sketch, then we can draw them in two dimensions as, let's say, a blue graph and a red graph. And then we interpret the inequality as the statement to solve for the values of x such that the blue graph is higher than or intersects the red graph. In particular, x squared being greater than 4 is identical to saying that the blue y is greater than the red y. And then that means that we're talking about height. Y is the height of the graph. So that we want to find the x values that make the blue graph higher than the red graph. Notice that we have x squared is greater than or equal to 4. And because we have the equation, we want the blue height and the red height to be the same. When we want the two heights to be the same, we are looking for intersection points in the graph. Now we have two intersection points, one at negative 2, 4, and another at positive 2, 4. So we have two x coordinates that we know for sure make this statement true. Furthermore, we can take a look at an infinite number of x values by scanning a vertical line, sweeping it across the graphs. The vertical line is an example of an x coordinate for which we can compare the red and the blue heights. In particular, right now we have at x equal to negative 1 that the red graph is higher and the blue graph is lower. We don't want that. We want the blue graph to be higher. Conversely, we could say that we want the red graph to be lower than the blue graph. Either way, this x value does not make the statement true. The red graph is higher and the blue graph is lower. So we're not looking for any of these x coordinates or x values in between negative 2 and 2. In fact, it may be helpful to come up with two vertical lines at x equal to negative 2 and another one at x equal to 2, which helps us to create some regions on our x-axis. I'm going to label this region 1, region 2, and then region 3. And so I can sweep my sample x-coordinate in all through region 1, and I notice that they have something in common. For every x-coordinate in region 1, the blue graph is higher than the red graph. And I want that to be the case. That satisfies my inequality. So I want all of the x values that are to the left of negative 2. Furthermore, in region 2, None of these x-coordinates makes my inequality statement true. The red graph is higher than the blue, and I want it the other way around. So I'm not going to choose any of these x-coordinates as part of the solution. Furthermore, to the right of x equal to 2, I notice that the blue graph is always higher, or the red graph is always lower. And so I'm going to choose all of the x-coordinates from 2 onwards. And so here I get that my solution is going to be the set of x values that are less than or equal to negative 2 or greater than or equal to 2. Another method that we can use to solve the inequality x squared greater than or equal to 4 is to take all terms to one side so that we have a function here, this x squared minus 4. I could refer to that as y equals f of x. And we want to compare the value of the function or the expression with 0. And a good model for understanding why this is a thermometer. We have the 0 degrees freezing temperature of water at y equal to 0, and then all of the positive temperatures are for y greater than 0, and all of the negative temperatures are y less than 0. So we are going to solve for x such that the expression value, the output, is either positive or 0. And so to do this, we are going to first of all find the zeros or the roots of the equation x squared minus 4 equal to 0. We found those as x equals plus or minus 2. The next step is to factor the expression or the function x squared minus 4, which in this case factors to x plus 2 times x minus 2. We do this because then we can look at combinations of the factors' signs, positive times negative, for example, and we will organize this information in a sign chart. I like to do it by setting up an x-axis. And on that x-axis, I'm going to put the two roots that I found, the negative 2 or the positive 2. And I'm going to create 3 regions from those 2 intersection points. And so this is helping me to create a chart. And I know that I have 2 factors, so I need 2 rows. And I'm going to write those factors of x plus 2 and x minus 2 here. Now coincidentally, I took the first factor of x plus 2 to correspond with the leftmost root. And then I took the next factor of x minus 2 to correspond with the next root as we increase from left to right or smaller to larger. What we're doing here now is to take a sample test value in each of the 3 regions. Again, this is the same region 1, 2, and 3 that we found using the graphical approach. We can pick any x-coordinate we want that is in each region. So I'm going to pick an x-coordinate of negative 3, then an x-coordinate of negative 1, and then an x-coordinate of 5. You can pick any numbers you like, 2.1, 2.01, a million, they would all work. And you're going to fill in the 6 cells of this table by substituting the x-coordinates into the individual factors. So let's substitute across the top row first. Negative 3 plus 2 gives negative 1, and I'm going to record a negative. The reason is I could have chosen any x-coordinate as long as it was to the left of negative 2. So for example, if I substitute negative 10, I get negative 10 plus 2 is negative 8. Or if I substitute negative 2.1, I would get negative 0.1. Both of those results are negative, and so I record a negative sign here. In the next region, region 2, negative 1 for x plus 2 gives positive 1, and I record a positive. And then 5 for x plus 2 gives positive 7. In the second row for the second factor, negative 3 minus 2 gives negative 5, then negative 1 minus 2 gives negative 3, and then 5 minus 2 gives positive 3. The goal then is to find out what happens if we multiply the quantities, the numerical values of x plus 2 times x minus 2 to get the function we were interested in exploring, the x squared minus 4. In region 1, any x value to the left of negative 2 will produce a negative times negative or positive result for x squared minus 4. The x values in region 2, positive times negative, make the output function x squared minus 4 value a negative quantity. And lastly, positive times positive gives a positive result for the function in region 3. We were looking for x values that made the function either positive or equal to 0, and so we know the zeros occurred at the roots negative 2 or 2. We also want region 1, which is to the left of x equals negative 2, or region 3, which is to the right of x equal to 2. And so our solution here is the same result we found using the graphical approach. x is less than or equal to -2, or x is greater than or equal to 2. In my next video, I'll show an alternative to the two different methods that I've shown here that help to speed up the process. Thanks for checking out Raelene Maths. If you like the video, click like and don't forget to subscribe to my channel.